So good morning, everyone. Today we are going to discuss water injection. And in the earlier, we compared the water injection with the gas injection. But now let's talk about a little bit more details about water injection. First, let me explain what we did for the experiment. This slide shows the experiment set up. Okay, here let's starting from here is you have a vessel here, you have a core. This is a core here. And then we need to do we need to do a half water injection. All right, so therefore we have to inject the water first, right? So what do we do here? Now, this is a pump. Okay, we're going to pump this one. You have water you got a water here and pump into this accumulator. It's called basically is a container to store the water. And then you have we pump the water goes through here and come to this line and go or have open here, open valve here, and then pump water here. So this process is half, okay? And then we close valve in this side, we open valve this side because after some time of water injection, the pressure inside is high, right? Okay, then we open this valve, so high pressure fluid will go out and accumulate produce the fluid in this container. All right, so that is a half a half procedure, one cycle. And then how to do the next cycle? And then we close this valve or keep this valve open. And then we pump water through this accumulator and into this container with a core plug. Okay, then we close this one, open this valve, and the high pressure fluid will be produced. So we repeat such kind of procedures. Then next, we need to find out how much water can be produced through such kind of half a puff process, right? So first, what we do is, so before we do the experiment, we first saturate it with the core. So we saturate with the core, which has the oil, okay? And then then after, like for example, after one cycle, and then we measure the weight of the core. In this, now core has oil plus water, right? So after one cycle. So some oil has been produced, but some water come in. So we measure this weight for each cycle. And then this total weight should be equal to the saturated weight, initial saturated weight, minus whole volume multiplied by oil density multiplied by oil recovery factor. So that is the oil produced weight. Right? So then what about this one? This is the pore volume multiplied by recovery factor multiplied by water density. So that is water entered water entered in the core, right? So therefore, so at each cycle, let's say at end of each cycle, the total weight should equal to the original weight minus oil produced plus water injected. That's the material balance, right? Okay, based on this material balance, in this material balance, we need to know the pore volume, VP, pore volume. How to get a pore volume? Pore volume will be saturated core weight minus dry weight of the core. That is the oil saturated, right? Divided by oil density, then that is the total oil in the rock, in the core plug. So then because initially we use oil to saturate this core plug, so oil occupy all the pore volume. Therefore, this oil volume is actually equal to pore volume. So now we get pore volume. Then we add this pore volume into the first equation and make some arrangement. So what do we got? This is recovery. This is oil recovery. So now we get an oil recovery factor. Let's look at whether we can measure oil recovery factor from the experiment data. Now let's say here is experiment at each cycle, we can simply measure it, right? Saturated weight, we know the weight before we do the experiment. So we also know that. And oil density, we know it, or we can measure it. Water density also known. Saturated weight, we know. Dry weight, before experiment, before the core plug is saturated by water or oil, any fluid is dry, so we know dry weight. So therefore, every single experiment is, every single parameter is known. So therefore, we can calculate oil recovery at each cycle, at the end of each cycle. Right, so that is experiment measure. Now, let's look at some experiment results. Here is the look at the effect of soaking time. For the gas in half a puff, we also, yesterday, we also talked about effect of soaking time, right? Let's look at the water half a puff. So now here is, this is a cumulative oil recovery factor, RF, and horizontal is for each cycle. Let's say for both this first cycle, second cycle. And here different curves for different soaking time. Let's say here is dark blue, dark purple one. This soaking time is 24 hours. And next one is 12. Next one is red one is 6. And the blue one is 1. Okay. So what do you say? At same cycle time, and of course, we all the operating conditions should be similar. For example, like injection pressure or half pressure is 1,000 psi for all the experiments. We only, in this set of experiment, we only change the soaking time. Okay. So let's say for each cycle, as the soaking time is longer, and then the recovery factor is higher. So this kind of experiment is consistent with what we observe for gas half a puff. Okay. So that is so this is the effect of soaking time. But we in this one, we did not compare we did not remember in the gas, when we talk about a gas, half a puff oil recovery, and we plot this recovery factor versus time. Do you remember? And if time, what I say is soaking time is shorter when and longer when. So T, let's say 0.5, remember? When 2 hours, something like that. So if the recovery factor is plotted versus time, operation time or experiment time, we find soaking time at the same time, soaking time has a negative effect. In other words, when the soaking time is shorter, actually at the same operation time, oil recovery factor is higher. This should be also true for water half a puff, but we're not going to spend too much on this one. Okay, well, I just simply review what we talked about yesterday about gas half a puff. And the same observation is observed for water half a puff, but I'm not going to present data in details. All right, so next one is, let's look at the effect of soaking pressure. Now in this time, soaking time is same, 12 hours. Here's a recovery factor and different cycles. Now what I can say is, this is green one, injection pressure is 5,000 PSI. Red one is 3,000 PSI. And blue one is 1,000 PSI. So this picture shows, this figure shows, and when the pressure is higher, or in soaking pressure or injection pressure, soaking pressure here is half pressure. Because at the end of the half, and then you stop the injection, that pressure is almost maintained at half pressure during the soaking time. So therefore we call soaking time, but it is also close to half pressure. I mean, we call soaking pressure, but it is close to half pressure. So now you can see the half pressure higher, recovery factor is higher for the same cycle. All right. Next, let's look at some field performance about water half a puff. So here the field, we have a vacuum and partial field, and we have a half time, about 1 month. Here is soaking time, is about 10 days, and production is 3 to 4 months. Let's first look at vacuum and performance. Let's look at our performance. Little or no oil increase, no injectivity issue. So that's from field results. So first, we have 2 observations here. First one is no injectivity issue. Why? What does it mean? Before we talk about this for gas and half, we also observed there was no injectivity issue for gas half a puff. Although we thought and shale reservoir is very tight, probably it is very difficult to inject fluid. But field test results shows there's no injectivity issue. Why? Do you remember how we explained this test results about gas half a puff? Do you remember? So we said, we explained, because shale reservoir has some micro fractures, although matrix permeability is very low. It's in the nanodarcy range. hundreds of nanodecibel range. That's typical matrix permeability. But we have many fractures because shear reservoir generally, when the first day, we explained when we look at a rock samples, what do we see? In the rock sample has some slot or secondary porosity, right? Now here we'll review what we talk about, we learned earlier. So all this secondary porosity or slot or fractures, whatever we call, will contribute to a higher permeability. So therefore, there's no injectivity issue. Okay, but there's no or little oil produced. So that is consistent with our only observation from simulation results. What do we see from simulation results? We saw gas half-puff oil recovery factor is much higher than that of water half-puff. That was from simulation result. But here from field data, we also confirmed this observation. Because in this case now, water half-puff, there was no oil or lead oil recovery or increase. Okay, let's look at another field. Second one, same thing, no oil decrease. Third thing, or no oil decrease. And in the third test, what is that? About 439,000 barrels of water injected first, then produced. Later, water alternative gas. Even what is the water alternative gas? Okay, so first let's just jump to the conclusion. Say there's no oil increase. That means no oil production increase. So either we use water injection or later on you even do the alternative gas. So it still does not water alternative gas. So what is the water alternative gas? Let me explain a little bit now about water alternative gas. Water alternative gas sometimes is abbreviated as WAG. You believe that WAG. Water alternate gas. What do you do? So first we inject the water, then followed by gas, then followed by water, then followed by gas. That means we alternatively inject the gas slug and the water slug. Okay. Why I want to do that? Why do we want to do that? And it is beyond that is conventional method. Let me simply just explain the idea, although it is not a focus of this course. So what I mean is, first, let's say, look at a reservoir. If we first inject the gas, let me use a single slide to, and so that I have enough space to explain. Let me do that. Let me use new slide. Okay, let's think about this big reservoir. If you initially inject gas, okay, you inject gas here inside. This is reservoir or layer, right? Reservoir layer. When they inject gas, what happens? Gas is lighter, right? So when the gas is light, here is water, is oil. Initially in the reservoir you have oil. So then gas is going to this what? You're going to go to top. That is gas. Because gas intends to flow to the top. Because its gravity is lighter, it will go up. Okay? Then what will happen? Say now if it continue goes, gas is going to like break through in the top. No oil can be displaced in the below, right? Okay, to do that, what about now later on we change it to water. Now let's say we change it to water. Now we inject water. So when water comes in, inject in the reservoir or in the layer, so water is heavier than oil, right? So then water is going down. So now water profile will be look like this one. Okay, so what happened now? So therefore some oil here can be displaced by water, but as oil in the top can be displaced by gas. And in the middle, probably displaced by, see, like doing this way, and then going to displaced by water and oil. So now what do you say? You have more oil is displaced by water or water and oil is okay. Oil can be displaced by gas and water. So from this description, what you can see that the water alternative gas injection looks like better than gas injection alone or water injection alone. So therefore, in conventional reservoir, WAG is one of the popular method to displace the oil. All right. All right. So now let's further look at the mechanism why water half a puff does not produce much oil. I will mention this one a little bit earlier, but now let's come back to this topic and give and have a deeper or better understanding. Now let's say look at here, incremental oil recovery from water and gas injection over primary depletion. Here is initially I presented this result earlier, simulation result. This is simulation data. Okay, half a puff. Okay, first is primary depletion. Recovery factor is low, 5.7. And then 20 years flooding, we have gas flooding, water flooding. Okay, gas flooding is better than water flooding. Half a puff and gas recovery, half a puff recovery is much higher than water half a puff oil recovery, which was presented earlier. Okay, now let's look at what caused this kind of result. Okay, here talk about the gas. This is left-hand side is the gas flooding. Is gas flooding pressure distribution. Right-hand side is the water flooding pressure distribution. Okay. And the red one means high pressure. Blue one means low pressure. Okay, now let's first look at gas. Gas here is, this is a high pressure region, this low pressure region. This is at end of 60 years. Now similarly, let's look at right-hand side is for water. Now this is the high pressure red area, right? High pressure, and after 60 years, pressure distribution. What do you say? For water flooding, for water injection, the high pressure region is much smaller than high pressure region in the gas flooding. So then, in other words, it is more difficult for pressure to push oil than the gas in the water flooding than in gas flooding. Okay, so that's one reason. Then water half-puff is, or water flooding is not as efficient as gas flooding. Okay, now let's look at half-puff. That's flooding, right? Let's look at half-puff. Now, here is the gas half-puff compared with water half-puff. In the left is, it's talk about this one is cumulative oil at different cycles. And this one is gas half-puff, top one, the bottom curve, and presents the data for water half-puff. Now, obviously, gas half-puff has, gas half-puff had higher oil recovery than water half-puff. So then, similarly, for the right-hand side figure, it also shows cumulative versus at cumulative recovery at different cycles. But the only difference is here is 6 soaking time, but the first left-hand side was 1 soaking time. The injection pressure was same, 1,000 psi. Okay. Now let's look at some water flooding project. Let's look at some more water injection projects, field projects. First one is water flooding in Bakken and low Shonova in Saskatchewan in Canada. So in this part, in this reservoir, porosity is 14. Porosity was 18%. Permeability was less than 1 millidascent. So this is matrix permeability. Okay, remember it's a millidascent range. Okay, then total 5 patents and 3 patents before. Total of the 5 patents in the Bakken and the 3 patents in this lower Shonova reservoir before 2011. So horizontal injectors paralyzed horizontal producers with 100 meters spacing. So this is a horizontal well were used in the field, and so distance is about 100 meters. Not 100 meters, hundreds meters. Okay, hundreds meters. And then history match recovery is about 1%. So in other words, 1.4%. In other words, this is recovery produced by pressure depletion. Okay. So then after 50 years, water injection. So here is basically, for example, here is the water injection, and here is probably producers. So after 50 years, the recovery factor is 5.1%. So in other words, 50 years oil recovery is less than. So here is it's about what? It's 5.1 is when it's 3.7, right? Okay, for 50 years. So now you can see 50 years recovery factor is 3.7%. If you are experienced engineer, you know it is a very low oil recovery. Now let's look at water injection half a puff. That is the first one was water flooding. Let's look at half a puff. Then this test, field test, was done by Marathon Oil Company. So bi-century field in McKenzie County, North Dakota, early 1994. They had 13,200 barrels of fresh water injected into a horizontal well for 50 days. And then the well was shut in for 2 months. This is soaking time. 2 months soaking time. So if you are experienced, then you know it is very long. So then after so long soaking time, oil rate was not raised. All right. So that also this field test also showed and half a puff water flooding did not work. Let's look at another one. Water injection pilot in Bakken in North Dakota. So this is first, let's look at the right-hand side and well arrangement. Let's see, all here is horizontal wells, all horizontal wells. And we have, in the middle, we have one injection wells, and all the 4 directions, the east, south, west, north, all have horizontal production wells. So only one injection well. Yeah. Then first stage injected 1,350 barrels per day for 8 months in the middle of 2012. And water rate, but not oil rate, increased in the east and the west producers. So then you injected here is 8 months, and the west and the east producers, you do not see oil increase. And then the second stage, so water stop for 6 months because there's no oil increase obtained or produced. So then you try different way. Let's stop water injection for 6 months. So that means the soaking time is about 6 months, right? Then it produce. What I was saying, water decreased, but not oil. Although water decreased, but oil was not increased. And the total 4,000 barrels of water injected, only 65,000 barrels of water produced. So now you inject this water is 444,444,000, but only what about? It's about 15% or 15% of something water produced. Most of the water is not produced, was not produced. Why? So then produced waters go to somewhere. Okay. So now again, you have such kind of earlier, we talk about a containment, right? For the gas, when we talk about a gas quality, we mentioned containment. So ideally for injected gas to be effectively producing oil, you need a gas injector should be contained near injection wells. Similarly, for the water flooding, for water injection, if the water is not contained near the injection wells or not near, and then it's going to be bricked bricked into the fire in the reservoir in the far away. So then oil cannot be effectively displaced by water. Okay, because water injection did not work in the later on, they converted this pilot into gas injection. Okay? Because the water was the injection did not work, so therefore they changed to gas. All right. Let's look at another example. Talk about water injection in Bakken, but in the Montana area. First stage in 2014, when injector and similar offset produced production wells. Water breaks through in 1 week. So in other words, water breaks through from injection wells to a neighbor production wells in 1 week. Water rate increased, but not oil. You see? So because water breaks through, more water produced, but no more oil produced. Water injection rate decreased later on. Water injection rate decreased later on. Now, second stage, in the early time, 2015, now circa 2 months, oil rate increased. Okay, so this test shows and the water soak help oil production. And why this have a soaking time, more oil produced? And this is caused by emission. We are going to talk about later on. I just simply mention it, and later on we'll talk about details emission. What is emission? We talked about let me explain here. We talked about it earlier. We learned about wettability, right? When the rock is water wet, what happened? So water will spontaneously enter the rock. Spontaneously enters rock. So this enters rock, water is water wet, right? Enters rock. So we call this phenomenon called imbition. Okay, I'll leave it. I'll keep it. If you have questions, keep it and just pay attention to my explanation tomorrow. Probably I'm going to talk about the imbition tomorrow. All right. Let's look at the water injection performance. Here, first column field and probability performance and reference. Let's look what are the field. We have Bakken, most of the Bakken, and some is in Russia, some in Alberta, Saskatchewan. All right, let's look at the probability. Less than 1 millidarcy, about 1 millidarcy, 0.1 to 5. Now is about millidarcy range probability. So what does that mean? Why I want to show that? That means probability not too high and not too low. It's not the typical shear probability. It's kind of low probability, or we call tight sand. So all this shows it is this field a tight sand or tight reservoir. Okay. All right. Was performance? First, Bakken, oil rate increase. Second one, no oil rate increase, low sweep efficiency. What is sweep efficiency? I can talk about later on, okay? And Bakken in Montana, water breakthrough issue. Water breakthrough right after water flooding. Oil rate peaked in first year, decline rate decreased. Oil rate did not increase, declined the decline rate. Okay, decline rate was declined, and low efficiency for injection wells. So from overall, what kind of picture you have? So it looks like some field tests showed oil increase, but more field cases showed water breakthrough problems. Okay, that is water breakthrough problem. So that is tight sand water injection performance. Now let's look at water alternative gas. Okay, earlier I explained what is the water alternative gas, right? Just a few minutes ago, I explained that today. And let me quickly show you a picture here. So that is the water alternative gas, or WAG. So this slide schematically shows the WAG. Okay, now let me further explain, add a little bit of more explanation about WAG. So probably when the probability is not too low, first, what is the WAG? W means AG is called water injection and alternatively by gas injection and continue on, right? So this is it's called flooding mode. Earlier, I mentioned what is flooding mode, what is a half a puff, right? So what is a half a puff, right? But this alternative WAG is a flooding mode. So therefore, when can you use flooding mode? When the probability is not too low. In other words, I mentioned earlier, for half a puff, probability for low probability is more effective. But for gas flooding, you need you should not use such kind of gas flooding in very low probability shale reservoirs. Probably is okay used in tight reservoirs. Okay, study shows high water gas ratio, higher oil recovery. So overall, that performance shows high gas oil ratio. Remember, when we talk about WAG, here is water, gas. What is the water gas ratio? Water gas ratio that means water slug volume divided by gas slug volume. So let's say it means this volume compared to this volume, okay? So that means high water gas ratio, high oil recovery. High gas water ratio, injectivity improved. If the other way around, if the high gas ratio or gas water ratio, and it's easier to inject fluid. And it also shows shorter slugs oil recovery improved. So that is WAG. Next one is I'm going to explain the pulse water injection. What is pulse injection? Water injection rate, sometimes completely shortening or injector. So in other words, you're injecting, you inject at a higher rate and then suddenly reduced rate, or even completely stop the injection. So you have a higher rate changes. Okay? In other words, rate change is high. So why we want to do that? It's like you try to use elastic energy. Like a spring, you initially press, then you release, press, release. So it's going to use elastic energy. Okay? Change the flow directions. Another mechanism is for such kind of pulse water injection is to change water oil injection in different times. Okay, so in other words, in first you inject your high rate, maybe water it's breaks through in some channels, and later on you suddenly you reduce and your pressure, your flow resistance will be changed, then maybe the water will go to other channels which was not flooded, which was not flooded earlier. That is the mechanism. And this such kind of test was done in China. It's this formation